Hello class. Today I'm going to show you how to solve this question. Okay, let's see what is this question about. We have a house with some parallel plates which are solar collectors with this let me show you. This is the solar collectors, each 1 meter width and 4 meter length. The plates are maintained at 15 degrees, so surface temperature is 15 degrees, while ambient air at 10 degrees. So ambient temperature is 10 degrees, surface temperature is 15 degrees, and we have ambient flows over the roof with 2 meter per second. Says determine the rate of convective heat loss, or Q, because of convection from the first plate for part A and third plate for part B. Okay. Like always, you need to first find what type of flow we have. So let's do that. I'm going to solve part A first. So let's see what type of flow we have. To find flow, I need to find critical lengths for this flow. As you know, Reynolds number, if it's critical, it's supposed to be velocity time length, which length? Critical length divided by nu. Therefore, critical length for this case is going to be critical Reynolds number multiplied by nu divided by velocity. From table, you need to find viscosity. So and viscosity is supposed to be for table from table A15. For which temperature? 10 plus 15 divided by 2, which is film temperature. And nu is going to be 1.448 times 10 power minus 5 meter square second. Okay. Now let's plug in the number. We know that critical Reynolds number for the flat surface is 5 times 10 power 5 times viscosity 1.448 times 10 power minus 5 divided by, what was the velocity? 2 meter per second, which is going to be 3.62 meter. So this is our critical length. For the first case, because as for the first plate and the flow is at this direction, so at this direction the length is just 1 meter for the first one, and the critical length is 3.6. so definitely we are going to have laminar flow. So let me write, therefore flow is laminar. Okay, we find flow. Okay, now I need to know what is the Reynolds number for that 1 meter plate or solar collector. So Reynolds number for that length is going to be velocity times that length divided by nu. So velocity is 2 meter. Which length? I just want to find for the first plate solar collector, which is 1 meter, divided by nu, which is 1.448 times 10 power minus 5. So Reynolds number is going to be 1.381 times 10 power 5. Okay, so now I need to find Nusselt number. Let's go back to the equation sheet and summary. These are the Nusselt number formula for flat surface. Okay, we know it's laminar, so we are supposed to be on the left side. Now we have a few choices. Is it local or averaged? So let's go back. The question says find heat transfer rate or convective heat transfer rate over first plate. It doesn't say find for x equal, for example, 0.1, 0.2, not for a specific point. It says for the whole plate. So we need average, and the average Nusselt number formula is this one. Let's go and write. So average Nusselt number. Sometimes we write just Nusselt number. Sometimes we write Nusselt number bar. So which is all means average. It's going to be 0.664 times, maybe just times Reynolds number power half times Prandtl number over 1/3, which is going to be 0.664 times 1.381 times 10 power 5 power half, and Prandtl number for the air, you need to also find Prandtl number for this, is supposed to be 0.733. So 0.733 power 1/3. So therefore, average Nusselt number is going to be 222.5. Okay. So we know whenever we calculate Nusselt number, we don't want Nusselt number, we want H. So let's calculate H. H for the first meter and supposed to be average is going to be equal K average Nusselt number divided by L for that 1 meter, which is going to be K for air is going to be, from table you need to find 0.0248 watt meter Kelvin. So 0.0248 times 222.5 divided by 1 meter, which is the length. This is going to give us 5.469 watt meter square Kelvin. So this is our H. Now we have H, we can do whatever we want. So the rest is finding Q dot. Maybe a little bit thinner. So Q dot is H for that one, and we know it's the average, A Ts minus T infinity. What is the surface? Let me write area of surface is, the length was 4 meter and the width was for 1 meter. 4 bar 1, it's going to be 4 meter square. So let's plug all the numbers. So H1 we found 5.469 times 4 meter. Surface temperature was 15. Ambient temperature was 10. So this is going to give us Q dot. For the first plate is going to be 109 watt. So heat transfer rate is 101 watt. So this is the general procedure we have for all convection questions. You need to check what type of flow we have, and then if flow is external flow, you don't need anything extra. You need to check if the question asks for local or average, find Reynolds number formula, find H, and then find Q dot or heat flux. Okay, what is part? This is part A. Part B says find for third plate, which is this one. Not number 1, not number 2, just third plate. Okay, so this is going to create a little bit challenge for us. Part B. For the third plate. Okay, let's see what we need to do. So this is my first plate, second plate, and third plate here. Again, because it asks us to find for third plate, which is this one, you need to have average. You need to find average convective coefficient H. But for which one? Just for number 3, not more for number 1 or 2. But we have a problem here. Let's go back. Check the definition of average heat transfer coefficient here. It says if you want to find average heat transfer coefficient, you need to integrate from the leading edge 0 up to the point you want to find. So for us it's going to be from 0 to 3 meters, and we integrate H for all that length. So if I want to use average heat transfer coefficient for plate 3, it automatically I'm going to integrate and find the summation of the all heat transfer coefficient from 0, which is here, to 3. This is 1, 2, 2. So from 1 to 3, which I don't want it. So what is the solution? I'm going to find from 1 to 2, from 0 to 2, from 0 to 3, and then subtract from each other. Let's see how it is going to happen. So let's find for the second plate. What is the Reynolds number for the second? It is going to be velocity, length for the second one divided by nu. Velocity was 2 meter, second one is 2 meter, and nu was 1.448 times 10 power minus 5. So Reynolds number is going to be 2.762 times 10 power 5. Still laminar flow. Let's find Nusselt number for the from 0 to 2. 0.664, Reynolds number 2, and Prandtl number over 1/3. 0.664, Reynolds number I just find 762, 10 power 5, power half, and Prandtl number was 0.733, power 1/3. And Nusselt number for up to plate 3 is going to be 314.7. And we know this is average. So average H for the second plate from 0 to second is going to be K Nusselt number 2 divided by L2, which is K was 0.0248 times 314.7 divided by 2 meters. And H is going to be 3.867 watt meter square Kelvin. Okay. Now let's find from 0 to 3 what is the Reynolds number for plate 3. Velocity, length for the number 3, nu, velocity was 2, length for, because I'm looking for the plate number 3, 0.448 times 10 power minus 5. It is going to be 4.144 times 10 power 5. So still laminar flow. And average laminar Nusselt number for 3 plates, it's going to be 0.664, Reynolds number 3 half, Prandtl number 1/3. 0.664, Reynolds number was 4.144 times 10 power 5 half, and Prandtl number was 0.7333. So Nusselt number is going to be 385.4, and because of this, the average convective coefficient is going to be 0.0424. 48 times 385.4 divided by 3. So it is going to be 3.158 watt meter square Kelvin. Okay. So let's see what I've done. So I calculated from 0 to 2, 0 to 3. Now I'm going to find what is H for between 2 and 3. So let's write it here. For example, I'm writing in pink. So Q between 2 and 3 is going to be Q for 3, which is from 0 to 3, minus Q from 0 to 2. So let's write the formula for this. H between 2 and 3 times, let me take it aside to have a bit of space. Times area which is going to be between 2 and 3, area is going to be 1 meter, because from 2 to 3 is 1 meter, times 4 meter length. Let's write 4, okay, times temperature difference delta T. It doesn't matter, so I'm just writing delta T. I don't want to put any value there. For this one, it's going to be H3. It is going to be 4 meters times 4 delta T minus. So let me, instead of writing their lengths, let me write L. This is delta T. L between 2 and 3 times 4, and this is H between 2 and 3. So here again, L3 times 4 delta T minus H for 2, L for 2 times 4 meters delta T. So let's get rid of similar items. Delta T, this 4. So what is going to be left is H from 2 to 3 is going to be equal H3 times length 3 minus H2 times length 2 divided by this length between 2 and 3. So this is my formula. Let's put the values. So H between 2 and 3, which I hadn't, now I can calculate it. H3 was 3 point something. H3 was 3.1. 3.158 times the length 3 minus H2 3.86 3.867 times the length 2 meters divided by the length between 2 and 3, which is 1. This is going to result in 1.739 watt meter square Kelvin. Now I have H, average H or convective coefficient for this area, for number 2 and 3, between number 2 and 3, or plate number 3. The rest would be very easy because I have H. Now Q dot is going to be H bar between 2 and 3, area between 2 and 3, and Ts minus T infinity. H bar is 1.739. Area is just 4 by 1. and surface temperature was 15, ambient temperature 10, so it is going to be 34.8 watt. Okay, this is our H, this is our Q dot. So let's see, our Q dot is 34 watt for the plate number 3. For plate number 1 was 109. Can you tell me why this happens? Maybe to answer this question, you can go back and check the graph for H, how it changed. Let me draw. This is my X, this is my H, and you know that the graph for H is like this. So gradually, at the beginning, very high H, gradually it is decreasing. So we expect to have smaller H and definitely smaller Q dot. Okay, thank you very much. See you next time.